Hi, this is Deka. So in a previous video, we actually computed the horizontal forces on this statically indeterminate system to the degree of 1. And for that, we used the force method. Okay, by the way, that first video was in English, and today I was just like, come on, just gonna do it in. And that first video was in German, sorry, and today I was just like, I'm gonna do this one in English, why not? And maybe we're gonna do a third one on these frames and then move on, okay? So what we're gonna do today is we're gonna compute one of those formulas again, but for a different system. So I'm gonna switch then to the book Schneider Portabellen, tables basically for civil engineers, and the one we've been using this for. And we're gonna do this second case here. So it still is a frame, it's still statically indeterminate to the degree of 1, and we have a single load acting there on the horizontal part. At the random position, basically, the length A is the distance between the load, the single load, and the left corner. So let's just do it. So I'm gonna take a screenshot of this system and the formula we're supposed to land at the end. And we're gonna compute it again with the force method. So let's do it. Let's just start. So what do we need? We need to draw the system again. The pin support on the left, the second pin support on the right. The frame corners are able to carry bending moments, the moment resistance, let's say like that. We have a single load F here, and the distance between the single load and the left corner should be A. Distance between the single load and the right corner, the right frame corner should be B. The span length is L, and the frame height is H. So let's get moving. I'm gonna use the same statically determinate system that we used in the previous calculation. So I'm basically gonna remove the horizontal load on the right pin support, turning it into a roller support. So in the, let's call it 0 load case, we're gonna have the chosen statically determinate system with the external load, so the force acting on it, the force F acting on it. And what we need to do is draw the bending moment diagram. So with no horizontal loads, we have a bending moment of 0 in the columns. And in the horizontal beam here, we're gonna have the following moment distribution with a peak at the position of the single load. Otherwise, it's linear. We can compute the vertical forces here and then calculate the moment, or just use the formula. It's like F times A times B divided by L. You do it. You can do it either way. You're gonna get to the same result. So moving forward, that's M0, by the way. Moving forward, we use the first unit case or first load case. where we apply on the system the load we had removed. So x1 is, I mean, it's not really 1 because we're gonna find the actual value of x1, but with x1 here, I'm just meaning the restriction that we had basically removed, or the force that we had removed. So we're just gonna put it back. So, and compute the bending moment diagram again. How's it gonna look? Well, this one, we've seen it already in the previous calculation. It's gonna be this one, right? With 1 times h here. Oh, I just got the notice that my battery is low. That's not a problem. So 1 times h. Just plug the computer in. It's gonna be fine now. So that's it. For the computation of the statically indeterminate reaction force, we're gonna need to compute delta 1 by basically coupling the bending moments of M1 with itself. Was it gonna be 1/3 for the triangle times h again times h, the length of the segment, so h to the power of 3 divided by EI, and I here is I for the column. Yeah, in German it's S for Ziel or Stütze. I'm just gonna use S again because the formula we wanna have at the end, well, it doesn't even have it. Yeah, because K was defined as something, and I'm gonna look up what K was. It was a definition for K. Here, K is IR times H divided by IS and L, basically. So that's the definition there for K. We're gonna use it. But R here is for Riegel, is name. It's used in German for that horizontal beam, and S is for Stütze, basically mean column, or you can also say Ziel is another word for it in this case. So I'm gonna just write it here. IA times H divided by IS times L, right? I hope it's R over S and not S over R. R over S and H over L is okay. It's okay, that's the formula. So this is just for the left column, for example, and then times 2 because the same thing's happening on the right column. And then for the beam, we're gonna have 1, that's the coefficient for rectangle times rectangle, basically, when you're coupling two rectangles. The value is 1 times H times itself, because we're coupling it with itself, this bending moment distribution. So squared times the length, L of the segment, divided by E, the Young's modulus, times I for the Riegel, or the beam in this case, okay? So that's it. That's basically a value we had on the top, on the previous calculation already. We should recognize it. This one, exactly the same, huh? Pretty correct, huh? So now we also need to couple the 0 distribution with the 1 distribution. So what are we gonna get? There's a formula for these two, is 1/2. Now the distribution on top is a positive one, and the one on the bottom is a negative one. So the sign is gonna be a negative sign. That one I don't know why I'm writing it in where it looks like it was a mistake or something like that. Let's just write it normally. So minus 1/2, and then the value on the top is FA times B divided by L. The value on the bottom on the M1 distribution is H. The length of the segment is L, or A plus B, that's L here, the span length. And so factor, first value, second value, length, yeah, and then Young's modulus times the second moment of area, or second or moment of inertia, whatever, second moment of inertia if you want, for the beam, or Riegel in German, right? So let's just compute this. L and L are gonna be cut out. So we're just gonna remain with minus 1/2 of FAB times H divided by EIR. There was an assumption in this whole calculation. We've seen it in the above case and in the first calculation we did of the art. The assumption is that the Young's modulus is the same for the whole system, which should not necessarily be the case in real life, right? But that's the assumption here. That's the EE. The Young's modulus is the same. Now let's compute X1 then. What's it gonna be? It's gonna be minus delta 1, 0 divided by delta 1, 1. We explained already why this, or how this formula comes to be. We explained it in the previous video, okay? So I would recommend you to listen to that one. That first video was in German though, so I hope it's not gonna be a problem, or at least you can refer to subtitles and stuff like that. But I don't know if it's actually done properly. I will probably need to translate it myself, I guess. So minus times minus, so they're just gonna cut themselves out, those two minus signs. So we have on the upper part 1/2 FA times B times H divided by EI Riegel. And on the denominator, we have delta 1, 1, so that's like 1/3 of H cubic divided by EIS times 2, okay, plus H square L divided by EI Riegel. No, I like that word. So that's an F, by the way. Pardon my not so beautiful handwriting, or not so good looking, whatever. Yeah, so now let's see how we're gonna put that K here in the equation. I'm gonna first I'm gonna remove those E, they're like disturbing me. So we're gonna multiply the numerator and the denominator times E. So those E are just gonna disappear. Good. Then what else? What else? I'm gonna send ER at the bottom. So basically I'm gonna multiply numerator and denominator times IR, I for the second moment of inertia. So what are we gonna get? This 1/2, I can send it down there. So we have like, oh wait, if I send it down, it's gonna be 4/3 H cubic times IR divided by IS plus 2, this 2, I just send it down. So I multiply times 2 here for the first element and times 2 for the second element. Okay, that's what I just did. And I multiply the numerator and denominator times IR, and that's what's happening here. A square L times IR divided by IR. They're gonna cut each other out basically. And here we have FABH. Okay, now let's take a close look to the end form we wanna get. You wanna have FAB at the top. You wanna have 3/2 in front, okay? And then for the rest, we're just gonna figure it out. There's an HL there too. Okay, we got it. We got it, we got it, we got it. So we wanna have 3/2. 3/2, okay. I have FAB on top. I don't want to have H on the top, so I'm going to remove H by dividing by H. both for the numerator and for the denominator. Otherwise, I will be changing the equation. I'm not allowed to do that. It needs to remain the same. Equals, so it needs to remain the same. I'm not allowed to change it. So I divide times h, I divide by h, sorry, at the numerator. I'm gonna do the same thing at the denominator. So we're gonna have like 3/3 here of h, h squared, then IR divided by IS plus 2 HL plus 2 HL, and the 2 IR are just gonna cut each other out. That's one thing. Now there's another thing I changed here, this thing here. I just wrote 3/2 here on the front. What does it mean? It basically means that I need to, one of the things I need to do at least is, oh, you know what? I'm not gonna put it here on the top. Not now. I'm just gonna leave it like this for the moment. So this is the current situation. After simplifying this equation, I'm gonna do it for different color. After simplifying this equation and multiplying both and dividing both the numerator and denominator by h. That's where we land. So now to have 3 on top, what am I going to do? I'm going to multiply times 3 here, the denominator and the numerator. I multiply the numerator times 3, then we get FAB. I multiply the denominator times 3, then we get 4h squared IL over IS plus 2, times 3, we said, right? Plus 6HL. So I don't need a bracket. So that's what we get after we multiply bottom and top times 3. Let's leave us here. Okay. So what else are we gonna do? We wanna have 2 here in front. So what are we gonna do? I'm just gonna write 2 there, and I'm gonna divide the rest by 2. I multiply by 2, I divide by 2, so I haven't changed anything. Or you can call it factorization. Factorizing 2 means we have 2h squared IR over IS plus 3HL here. And on the top, at the numerator, we have 3FAB. We're almost there. What's left? We want to have H times L here. Look at the end form we're looking for. What's missing? H times L. So we're just going to put H times L outside of the brackets. How do we do that? Well, putting H times L in front of the bracket basically means that we multiplied here times H times L. And to keep the fraction unchanged, we're gonna have to divide the elements inside the bracket by H times L. So what are we gonna get? 2H IR divided by L IS plus 3. H times L divided by H times L equals 3. What we did here is we divide by H times L. Both on, no, not really, both on top and, well, you can actually say that. You can it's not exactly what we did, but at the end, it's also what we did. And you can say that we did 3 FAB divided by HL, and then what would that mean? That you have 3 FAB at the numerator, and you can write HL at the bottom, this one. And then for the denominator, we divide by HL. That's the operation we did in here. And so you can look at it either way. You can say that we divide the numerator and denominator both by H times L, or you can say that here in the front we multiply by H times L, and in the brackets we divide by H times L. It doesn't matter how you look at it. The result is the same. and it's equally correct mathematically. So 3 FAB. So what's left? We know this friend here, IR divided by IS times H over L. Well, in those Schneider tables, they decide to call it K for whatever reason. I mean, it's a factor that, yeah, that's only dependent on the geometry and the material parameters. Actually, I want to say the geometry because I it's not really a material parameter. It's a parameter from the cross section. Along with the cross section, you can compute I, the second moment of inertia, or second moment of area, actually, or moment of inertia. Actually, I don't really like the word moment of inertia because there's another physical entity that we call mass moment of inertia that we use in dynamics and stuff. And when we just call this moment of inertia, I'm a little bit disturbed. Yeah, anyway, that's it. We have 3/2 FAB divided by 2K, okay, plus 3. And that's exactly the formula you have in Schneider. So that formula is also correct. And that's X1, and X1 is nothing else but H2. H2, by the way, is supposed to be the horizontal craft acting here to the right, and H1 would be this one, the one on the left acting to the right. So that's it. Thank you for your attention. We confirm that this formula is correct. It's been available in the Schneider table for ages now. So good to know that it's correct, and see you next time for maybe one last of those calculations on frame systems, and maybe we're gonna, not maybe, we're probably gonna move to something else. I have like enough to do here. I hope this was a pretty nice revision of the force method. The force method was explained already on the channel, both in German and in English. You have the possibility to check those videos out if you've missed any of those. In the meantime, I'm just gonna say, yeah, see you next time. And thank you for your attention as always.